Hi everyone, welcome to the last talk, and again, you can submit questions from the internet.
Good afternoon, everyone. This is joint work with Casper, Bach, Poulsen, Andrew Tolmach, who's here, Robbert, Krebbers, also here, and Eelco, somewhere. And this work is about defining semantics for languages in such a way that we get a specification that is executable first, so that we may understand and test the adequacy of the specification through testing. And we also really want a concise and understandable specification, because we will be reading those. We want the specification to be maintainable, because the language will develop. And of course, we want it to be type safe. Now, one such way to get an executable first specification of semantics is to define it by an interpreter. And if you pick your host language right, these might be concise and understandable specifications. But there is some friction between being maintainable and being safe if you get safety through an extrinsic type safety proof. Because you have this extrinsic proof that will develop alongside with your specification. Now, luckily, the guys doing dependent types, you know that there's an alternative way to get safety in an intrinsic way, namely, and the recipe for that is something like this. So you define your types as a set, then you define the syntax of your object language in a typed way, where you index this expression type with your object language types. And the constructions of this type will basically merge the syntactic rules with the typing rules. Besides adding information to the syntax, this also constrains your syntax to the well-typed fragment. Now you do the same with your values, and then you have all the ingredients to express what a type-preserving evaluation function is. So this evaluation function takes only well-typed expressions and will produce values with the same type as the input expression. Now the real appeal of this approach can be seen if you look at a simple definitional interpreter that is typed in this way. Because even though we're simultaneously defining semantics and proving it safe here, this just looks like an untyped interpreter. And we really get this integrated type safety check, where the host language can check that we're preserving types properly, and this pattern match that would, in an untyped interpreter, would be partial, is actually seen to be total in this case, which is nice. Now, the main question of this paper is, can we take this approach, which seems to be appealing for simple cases, and scale it up? It seems to be well known how we can do simply typed expression languages, and languages that have maybe lexical lambda binding. And then there's work by others on scaling this along the axis of fancier type systems. But if you look at features such as non-lexical binding in languages and imperative state, then it's unclear how to treat these. So that is where our main contributions are. We give a object language parametric Agda library for dealing with non-lexical binding and its runtime counterpart monotone state. Structured memory. And then we define and show how to program with a monad for monotone state, so we may safely interpret imperative state. And then we evaluate both of those technical contributions in light of a case study, which is, as far as we know, the first intrinsically typed semantics for an imperative language the size of Middleweight Java. Now, these two technical contributions are, in essence, orthogonal, so we'll treat them in turn, and I will try to illustrate how they complement each other using simplified examples from our case study. Now, let's have a look at binding first. So, like I said, it seems to be rather established how you deal with lexical lambda-style binding in these interpreters using well-typed de Bruijn indices. But if you look at non-lexical binding, nothing is as established. But there is work by Pierre Neron and others on describing both lexical and non-lexical binding in a uniform way using scope graphs. And we'll use this to define well-typed syntax for languages with non-lexical binding. Now, how does it work? We may consider how you would use scope graphs to describe the simple binding structure of a lambda term. So in terms of scope graphs, we would say this lambda term has two scopes, one for each binder, and both binders introduce a single declaration, which is types. And then there's the single reference, which in this case is well bound, because there is a path from the inner scope to the declaration with the same name and type. Now you can also represent this lambda term in a nameless style, which would correspond to dropping all the names from the scope graphs, and just represent the well-bound variable using the path, the structure of the path from the inner scope to the declaration. Now, just as typing context induce environments at runtime, scope graphs induce structured memory at runtime, in such a way that for every lexical scope in the scope graph, we will get a call frame. And when we have paths denoting well-bound variables, we can look them up safely on the structured heap, starting in the call frame that instantiates the scope in which the path was originating. Now, we've used a very general syntax of graphs to describe this very simple binding structure, and so you may imagine how this could generalize. We could have scopes with multiple declarations, and we could easily have scopes with multiple parent scopes. And we can use that more expressive power to describe the binding structure of a simple class hierarchy as it appears in Middleweight Java. In Middleweight Java, classes are defined in the top-level scope. So we'll have a program scope, and we'll have two declarations in this case for two classes A and B. Now, the classes have structure, of course, so we'll associate these declarations with scopes that describe this structure in such a way that we have declarations in these scopes for the fields and methods that these classes define. Now, in this case, the class B also extends to class A, meaning that all the declarations of A will become visible through B. And we can make this apparent in the scope graph by adding in an edge that denotes this inheritance. And finally, if we have lexical structure beneath this, such as in the methods, we would build this on top of this scope graph. Now, just like we had lexical frames or call frames on the heap instantiating lexical scopes, these scopes that describe class structure induce frames on the heap. Yeah, in much the same way. Now, with this picture of scope graphs, let's consider how we may define typed syntax for languages with non-lexical binding, in this case in the host language Agda. Particularly, we will look at this statement in Middleweight Java, which is slightly simplified, for assigning to a field on an object. Now, statements in Java do not return values, so this particular well-typed syntax is not indexed by a type, but it is indexed by the lexical scope in which the statement appears. Then the assignment constructor will quantify over yet another scope, which will describe this class structure of the object that we're going to assign to. The first thing we want to witness is that the object expression is typed by this class described by B. We then want to use a well-bound name to represent the field that we'll be assigning to. And for that, we'll use the type of paths that start in this scope that describes the class and end in a declaration for the field. Now, because we've witnessed inheritance with an edge, this might either be the local field on the class or it may be inherited. Well, then we have an expression on the right-hand side that should match the type of the declaration. And finally, we have the remainder of the statements that are typed in the same lexical scope as this statement, because we haven't added any binders in this particular example. Now we may consider how we can interpret this. We do that with an evaluation function that takes the statement in some lexical scope. It also takes a heap under which we're interpreting, and it takes a witness that we have on this heap a frame for the lexical scope in which the statement appears. Now we're then interpreting the object expression first, and we're threading a heap because expressions in Java are side effectful. And because this is a typed interpreter, we'll get a value that we know represents this object, which will contain a witness that this heap also contains a frame with all the object data. We then interpret the right-hand side of this assignment and get a value, and may then finally update this object. And for this, we'll use a function from the library that we've defined for manipulating these well-typed heaps, typed over scope graphs, set value. And this is well-typed and safe because we know that we have a frame that instantiates the scope that describes this class. We also know that we have a field that is visible in this class because it's typed as such. And we have a value that matches the declaration of this field. And then finally, we may interpret the remainder of the statements in the same lexical frame. Now I think this demonstrates well how we define syntax over scope graphs and how we may interpret those safely using heaps that are typed over those scope graphs. But this doesn't quite type check in Agda. And the reason for this brings us to the second problem that we address in this paper and the second contribution, which is about threading monotone state. So the problem will become apparent if we consider how these heaps are actually typed. So to make sure that we have safe pointers, we index all of our stores and frames with a store type that describes the entire structure of the heap. But as we interpret bits of syntax and we get updated heaps, we get also updated store types, and this is, well, it develops in an existentially quantified way, right? So because we're doing ML reference style state here, the type system doesn't describe what the post store looks like. And then we run into the problem that if we hold an updated heap in one hand and we have an old frame pointer in the other hand, we don't know that we can safely dereference this in the updated store. Now, the intuition of why this should be safe is that we're using monotone state, so we're only growing the store, and old references should remain valid. And we can type check this program again by making that assumption explicit. So every time where we update a heap, we also return a proof that this heap is an extension of the old heap. And then we can recon all of our pointers appropriately. But this leads to quite a bit of syntactic noise, as you can see. And this kind of conflicts with our requirement that we want a concise and understandable semantics for object languages with imperative state. So in the paper, and the other thing that makes this thing more noisy than necessary is, of course, that we're manually threading these heaps. So probably a few of you are already wondering why we're not doing a monadic style interpreter. And indeed, if we do write this in a monadic style, then we get a much cleaner interpreter where we've put the heap that we're interpreting under in the monad as well as the lexical frame. And now the monad can do the weakening of this lexical frame for us. But any value that we'll bind on the left-hand side that depends on the heap type and that we carry across another bind and then use it, we'll still suffer from this typing problem. And now it seems that we'll have to expose these extension facts again through the binds and manually weaken these pointers. But in the paper, we propose a more elegant solution, which is to use what is essentially the strength of this strength operator of the strong monad to carry these type pointers across binds. So we may safely use it in an updated heap. Now we believe that this interpreter has all of the properties that we like. It is, of course, executable because it's an interpreter. It's still concise and understandable. And it's maintainable because we don't have this extrinsic proof. And finally, it's type safe by construction. And why is this the case? Well, we believe that it's because we have written this in a we call it dependent passing style, using the strength operator, and also because we have a library for lightweight manipulation of non-lexical binding. Right. Now, a higher level overview of the results in this paper has been tried to capture in this table. So we have our MJ semantics on the right, which is intrinsically typed, and then we have the three other mechanized semantics of Java subsets on the left, and these are all extrinsically proven safe. Now, these are different subsets, and they're proven in different systems using different methods, so you may not directly compare line counts, but what you can see is that the majority of the lines of code go into the extrinsic safety proof for all three of these mechanizations. That is 75 to 80%. Not only do we not have this extrinsic artifact in our case, it also seems that we haven't just moved all of the burdens to the intrinsic definitions. But yeah, we really get these concise, type-safe by construction specifications. Now, in this work, we've focused on defining these definitional interpreters that have these properties that we like for more interesting languages than we could do before. In future work, we try to see if we can do this as well for even richer languages, languages with more effects, or languages with fancier type systems. And we're also interested in figuring out if we can verify other interesting language properties in a similarly integrated way. Now, if this has made you curious to the real semantics that we've defined for Middleweight Java, then I want to encourage you to have a look at our artifact, which is on GitHub. We spent a lot of effort trying to make this approachable, even if you don't have an Agda environment set up. So go have a look. Thank you.
Do you have the termination checker in Agda turned off to check your definition?
No, but we are fueling our interpreters to get them through.
Okay.
So what if you want to prove some property extrinsically? Did you try to prove something about this semantics?
So if you want to prove?
I mean, you've defined your definitional interpreter. Did you try to prove some properties about this just to see if it's feasible?
No, so that's also something that we like to consider in future work, if we can do other meta theory besides this. Yeah, but the focus has really been on type safety.
So one of the standard difficulties with intrinsically typed encodings is dealing with languages where you could have multiple representations of the same type. Does this have any insights for that? For dealing with, int versus identity applied to int?
Right, yeah, so what you usually see in those is that you get syntactic forms, additional syntactic forms in those languages for conversion, right? No, we don't have any new insights on that area. Yeah.
So does this intrinsically typed interpreters, does this also deal with languages that have like unsafe features? So how would it deal with this?
I think you can put this in the category of a very syntactic proof method. So I don't think we contribute anything there, no.
Follow up on my question as I was thinking about the answer a little more. You do seem to effectively have recursive types with the way classes work, or at least if they work the way I'm used to in Java, where I might define a class with a field whose type is the same class itself. So then I wonder how you write down the type of that. Just having a fuel for the interpreter wouldn't seem to solve that problem.
Right. So the syntaxes are typed over a global scope graph. So you know beforehand what scopes describe what classes, and we can use those to represent the types.
Okay. It seems like there's a free lunch somewhere with having general recursion in type theory, but I guess I should ask you more offline.
Okay, yeah. So every time where you hold a value that is indexed by this heap type, and you want to, the question was, how do you know where to use this caret operator, this strong operator? So you have to use it every time you want to carry, you have a value that is indexed by this heap type and you want to use it across another bind.